G'day viewers. In this episode we are going to extract electromagnetic radii solution from Tshipa's particle-antiparticle pair representation. We demonstrated in episode 98 that Tshipa's PAPPR construct only applies to point particle solutions whereby spin angular momentum and electromagnetic radii solutions are not explicitly defined or addressed. However, by utilising the electrogravimetric EM radii solution as a template, the PAPPR construct may be reconfigured into generating EM radii, producing the following results. Number 1. The neutron mass moment of inertia configuration coefficient satisfying a neutron charge density of 0 equals 0.663. Number 2. The neutron mass moment of inertia solution we derive implies a positive core encased by a negative shell. This is consistent with standard nuclear theory. Number 3. The neutron mass moment of inertia solution we derive implies spheroidal geometry. Number 4. The proton and neutron magnetic radii for the PAPPR construct is given by a holosphere neutron solution such that PAPPR EGM similarity is greater than 99.92%. Number 5. The proton electric radius for the PAPPR construct is given by a point particle neutron solution such that PAPPR EGM similarity is greater than 98.99%. Number 6. The neutron mean square charge radius for the PAPPR construct is given by a hollow spheroid solution such that PAPPR EGM similarity is greater than 99.99% and PAPPR experimental similarity is greater than 99.68%. So, by utilising the EGM electromagnetic radii solution as a template, the PAPPR construct may be reconfigured in order to generate electromagnetic radii. Okay, let's get into it.
Let's begin our journey by identifying where the Tshipa research article can be found, as we did in episodes 98, 99, 100 and 101. Now that you know where to find the primary artifacts, let's expand Tshipa's particle radii model to electromagnetic solutions. If you have not already watched episodes 98, 99, 100 and 101, please pause this video presentation and watch the previous episodes before proceeding. Moreover, we strongly encourage viewers to review the Storti 2007 research article listed and the proton and neutron video presentation appearing on our channel. Please refer to episode 5. Well, assuming that you have followed my instructions, let's review Tshipa's results from episode 98. Tshipa's results contain 3 columns of quantitative information, that is, his calculated radii, the radii from a literature review, and the percentage deviation between them. As you can see, we have boxed the column containing the radii values from Tshipa's literature review. Why have we done this? Well, we have done this because no direct connection exists between Tshipa's calculated radii values and the electromagnetically associated radii values obtained from his literature review. Although Tshipa's results appear impressive upon first exposure, closer scrutiny reveals that there is nothing in Tshipa's particle radii derivation process which associates the form of radii appearing in the nomenclature with his calculated radii. In other words, as presented, Tshipa's calculated particle radii appear to be incomplete or unfinished as they do not infer any like-for-like association with the literature review results. Tshipa does not reconcile the physical meaning of his radii results against charge radii, magnetic radii, electric radii, or simply radii. Let's now compare Storti's particle-antiparticle pair representation results to Tshipa's results. Storti's particle radii results present 4 significant features against Tshipa's formulation as follows. Number 1. Storti's results match Tshipa's results precisely. By inspection, we can see that any differences between them are trivial and may be discarded. Number 2. Storti's particle radii equations do not contain any electric or magnetic terms. Number 3. Storti's particle radii equations do not contain any spin angular momentum term. This is extremely important because it invalidates Tshipa's propositions regarding particle spin and helicity. Number 4. Storti's particle radii equations do not contain a mass moment of inertia term. This means that all baryons, mesons and bosons presented may be modelled as point particles where the mass moment of inertia configuration coefficient I sub x equals 0. As appears on the right-hand side of Table 2, we have averaged the radii values stated in Tshipa's research article. Moreover, we have concatenated the particle radii description obtained from Tshipa's literature review. By executing these changes, we are able to succinctly emphasize the lack of like-for-like association between Tshipa's calculated particle radii and his literature review results. So, as we can see on screen, Tshipa's results have been reproduced precisely via a point-particle solution derived by Storti. This means that Tshipa's particle-antiparticle pair representation does not contain any electromagnetic radii information. In order to extract electromagnetic radii information from Tshipa's model, we will need to look at how Storti solved the problem in 2005. Let's begin by providing some context. In 2004, Hammer and Meissner executed a theoretical investigation in order to decompose specific properties of the proton and neutron, termed electromagnetic form factors. They established an estimate for the neutron magnetic radius, proton magnetic radius, and proton electric radius. Similarly, in the following year, Storti also derived estimates for these properties, as shown. Storti concluded that, number 1, the National Institute of Standards and Technology root mean squared charge radius for the proton and the proton electric radius are the same measurement. Number 2, the Selex collaboration root mean squared charge radius and the zero-point field equilibrium radius are the same measurement. Number 3, the proton magnetic radius coincides with the neutron magnetic radius. Number 4, the neutron magnetic radius coincides with the zero-point field equilibrium radius. You can see the MathCAD computational algorithm and the associated numerical solution appearing in the red box. However, let's take a look at the exact analytical solution and the equations involved. Utilizing the principle of zero-point field equilibrium, Storti derives exact analytical solutions for the root mean squared charge radius of the proton, the mean squared charge radius of the neutron, and the minimum charge density radius of the neutron. The significance of this being that Storti's radii derivations have been experimentally verified to extremely high precision. Moreover, the electrogravimagnetic construct solves the standard model of particle physics problem of a negative quantity being associated with neutron radius. The fact that the standard model of particle physics does not and cannot express the mean squared charge radius of the neutron as a simple positive length measurement is indicative of an incomplete method. Utilizing zero-point field equilibrium radii, Storti determined the proton electric radius, the proton magnetic radius, and the neutron magnetic radius, whereby Storti's solution predicts the two magnetic radii to be equal. However, at our present level of technology, the neutron mean squared charge radius, proton magnetic radius, and neutron magnetic radius are experimentally indistinguishable from each other. The final hurdle Storti overcame was the significant difference between the value of root mean squared charge radius adopted by the National Institute of Standards and Technology and the value experimentally measured by large colliders as utilised by the Selex collaboration. Storti proposes that NIST have misidentified their 2022 value of proton root mean squared charge radius. That is, it actually represents the proton electric radius. Okay, let's now graphically visualize the EGM electromagnetic radii solution. In order to visualize the electrogravimagnetic radii solution, we firstly need to visually understand the neutron charge distribution curve and where the neutron mean squared charge radius and the neutron minimum charge density radius sits on the curve. Appearing on screen is a graph of the neutron charge density versus radial displacement, with points of significance circled. It should be noted that this charge distribution curve, which has been derived utilizing the EGM construct, was experimentally verified by Juzo Zenihiro from Kyoto University in 2011 as part of his doctoral dissertation. The experiment was performed at the Ring Cyclotron facility in the Research Center for Nuclear Physics at Osaka University. Three important features of the graph are as follows. Number 1, the neutron mean squared charge radius, R sub nu, coincides with an effective value of zero charge density and crosses the x-axis as indicated. We will cover this point in more detail on the next slide. Number 2, the minimum charge density radius coincides with R sub dr as indicated. Number 3, Standard nuclear theory considers the neutron to consist of a positive core encased by a negative shell. As is clearly indicated on screen, the EGM solution aligns precisely with standard nuclear theory, that is, a positive charge density transitions to a negative charge density. Hence, we can see mathematical and graphical evidence of a positive core encased by a negative shell. Okay, let's now take a look at the zoomed view indicated on the next slide. Numerous important features exist in this zoomed view. By studying the graphical output, we can see that the neutron magnetic radius equals the proton magnetic radius, and both phenomena yield zero charge density at the same radii. The zero-point field equilibrium radius, r sub nu, equals the mean square charge radius, which also appears as r sub nu. Hence, r sub nu denotes two equivalent properties. The difference between the neutron magnetic radius and the neutron mean square charge radius is approximately 86 yoctometers. This means that we cannot technologically differentiate between them. Similarly, the proton magnetic radius is technologically indistinguishable from the neutron mean square charge radius. Hence, the neutron magnetic radius, proton magnetic radius, and neutron mean square charge radius are effectively co-located. Thus, we can confidently state that, within observational tolerance, the neutron charge density at all three radial displacements is either exactly zero or effectively zero. In episode 5, we propose that the 2022 proton root mean square charge radius, as published by the National Institute of Standards and Technology, and our proton electric radius are the same measurement. In other words, we propose that NIST has mistaken the proton root mean square charge radius for the proton electric radius. The required observational tolerance to distinguish between them is approximately 6.8 attometers. Okay, by utilising the EGM electromagnetic radii solution appearing on screen as a template, let's now visualise the particle-antiparticle pair representation of electromagnetic radii. Here is where the particle-antiparticle pair representation gets interesting. We demonstrated in episode 98 that the PAPPR construct, as originally formulated by Tshipa, is a simple point-particle model. Although Tshipa claims correspondence and comparison to electromagnetic radii in his results, this is not actually the case. We have conclusively proven over several video presentations that Tshipa's PAPPR construct requires considerable development in order to satisfy the implied claims in his table of results, which appear as Table 1 in this video presentation. Tshipa's PAPPR construct does not organically include any electromagnetic radii information. However, the electrogravi-magnetic construct is capable of extracting EM radii information from the PAPPR construct. In episode 99, we derived a particle radii solution incorporating spin angular momentum information. Consequently, in episode 100, we utilised this spin angular momentum information to derive an up and down quark form factor solution, in which we concluded that the geometrical shape of up and down quarks is spheroidal. We also acknowledged in the same episode that the up and down quark form factor solution should mimic the environment in which these quarks reside. Hence, the following three modelling expectations may be validly applied. Number 1, a solution involving a point particle is to be expected. Number 2, a solution involving spin angular momentum is to be expected. Number 3, a solution involving spheroidal geometry is to be expected. Utilising hollow sphere neutron geometry as an initial configuration, we developed a MathCAD computational algorithm which satisfies the zero neutron charge density condition. Our computational algorithm yields the following results when the neutron charge density equals 0. Number 1. The mass moment of inertia configuration coefficient equals 0.663. Number 2, the mass moment of inertia solution, I sub x equals I sub nu, implies a positive core encased by a negative shell. This is consistent with standard nuclear theory. Number 3, the mass moment of inertia solution, I sub x does not equal 2/3 because I sub x equals I sub nu, implies spheroidal geometry. This is consistent with the up and down quark form factor derived in episode 100. Number 4. Our results imply that the proton and neutron magnetic radii within the PAPPR construct may be articulated as appears on screen. As we can see, the correlation to the EGM result is astonishing. The similarity between the PAPPR and EGM results is greater than 99.99%. Utilizing point-particle neutron geometry, we obtain a proton electric radius solution. This makes intuitive sense because, number 1, a point-particle solution does not contain any spin-angular momentum properties. Please refer to episode 98 for more information. Number 2, in the absence of spin-angular momentum properties, a point-particle solution is non-rotating and should not produce a magnetic field. Hence, it follows that only an electric field will be produced and consequently only an electric radius will be generated. Thus, point-particle neutron modelling is dynamically, kinematically and geometrically similar to point-particle proton modelling. In addition, the mass-energy and quark similarity between protons and neutrons implies the existence of broader similarity. Number 3, our proton electric radius demonstrates greater than 98.99% similarity between the PAPPR and EGM constructs. So then, what does the National Institute of Standards and Technology value of proton root mean squared charge radius mean in the context of the PAPPR and EGM constructs? Well, the NIST value of proton root mean squared charge radius is in direct conflict with the result experimentally determined by the SELEX collaboration. Although the SELEX collaboration measurement is a 2001 value, which may seem to be outdated by some viewers, we must remember that it is a physical measurement, hence it does not have a use-by date. It is also important to recognise that the NIST value of proton root mean squared charge radius is historically transient. In other words, the NIST value of proton root mean squared charge radius has varied over time. In 2002, the NIST value of proton root mean squared charge radius was 875 atometers, not the 2022 value of 841.4 atometers as appearing on screen. This variation over time occurs because NIST proton root mean squared charge radius estimates include theoretical solutions as well as physically measured data. I shall emphasise that, over time, the NIST value of proton root mean squared charge radius is moving towards the 2001 SELEX collaboration measurement. Okay, so what's the bottom line? Well, the difference between the value of proton root mean squared charge radius adopted by NIST and the value experimentally measured by large colliders as utilised by the SELEX collaboration implies that NIST have misidentified their 2022 value of proton root mean squared charge radius. That is, it actually represents the proton electric radius. Please refer to episode 5 for more information. Let's now look at how the size of the neutron according to the PAPPR construct fits in with standard nuclear theory and the traditional method of calculation and representation. An important metric in standard nuclear theory is neutron mean squared charge radius. This is the most common reference to the size of a neutron and is expressed as a negative squared quantity, that is, typically negative femtometers squared. The historical calculation of neutron mean squared charge radius is given by the Foldy term, circa 1958. The Foldy term may be converted into an intuitive form, approximately equaling 872 atometers. Inclusion of the Dirac form factor yields the experimental value of neutron mean squared charge radius expressed as a negative squared quantity. Once again, this may be converted into an intuitive form, approximately equaling 826 atometers. By inspection of the results appearing on screen, we can see that the PAPPR model fits the EGM construct and experimental observation extremely well, with the hollow spheroid solution denoting the best overall fit. Okay, let's now summarise what we have learned. Although Tshipa's results appear impressive upon first exposure, closer scrutiny reveals that there is nothing in Tshipa's particle radii derivation process which associates the form of radii appearing in the nomenclature with his calculated radii. In other words, as presented, Tshipa's calculated particle radii appear to be incomplete or unfinished, as they do not infer any like-for-like association with the literature review results. Tshipa does not reconcile the physical meaning of his radii results against charge radii, magnetic radii, electric radii, or simply radii. However, by utilising the electrogravimagnetic electromagnetic radii solution as a template, the particle-antiparticle pair representation may be reconfigured into a construct capable of generating electromagnetic radii. Once completed, we obtain the following results. Number 1. The neutron mass moment of inertia configuration coefficient satisfying a neutron charge density of 0 equals 0.663. Number 2. The neutron mass moment of inertia solution I sub x equals I sub nu implies a positive core encased by a negative shell. This is consistent with standard nuclear theory. Number 3. The neutron mass moment of inertia solution I sub x does not equal 2/3 because I sub x equals I sub nu implies spheroidal geometry. Number 4. The proton and neutron magnetic radii for the PAPPR construct is given by a hollow sphere neutron solution such that PAPPR EGM similarity is greater than 99.92%. Number 5. The proton electric radius for the PAPPR construct is given by a point particle neutron solution such that PAPPR EGM similarity is greater than 98.99%. Number 6. The neutron mean square charge radius for the PAPPR construct is given by a hollow spheroid solution such that PAPPR EGM similarity is greater than 99.99% and PAPPR experimental similarity is greater than 99.68%. Thus, as our summary demonstrates, by utilising the EGM electromagnetic radii solution as a template, the particle-antiparticle pair representation may be reconfigured into a construct capable of generating electromagnetic radii.